Welcome to the SIRE 2.0 inspection program and to the third module in this series of technical videos. In this module, we will cover the risk-based approach taken by a SIRE 2.0 inspection and the use of the bow tie methodology to generate a bespoke risk-based vessel inspection questionnaire. This video will give you a greater insight into the technical aspects of a SIRE 2.0 inspection process. We will look at the concept of the risk-based approach used in the development of the question sets, the ranking of questions based on the risk that they address, the use of the bow tie methodology, and the question types. Let us first look at how we set about bridging the gap between a SIRE VIQ7 inspection and a SIRE 2.0 inspection. To do this, we must first remind ourselves of the characteristics of the current SIRE inspection based on a VIQ7 questionnaire. The question style requires a binary response. The questionnaire contains a large number of questions, too many questions being answered as not applicable. This is a paper-based inspection. The questionnaire provides limited guidance to the inspector. The question sets are fixed for every inspection. A risk-based approach to SIRE 2.0 inspections will mean inspectors complete a compiled vessel inspection questionnaire (CVIQ) that is generated using a sophisticated algorithm to create a bespoke questionnaire for each inspection. The inspection will be completed in real time using a tablet device. The key features of a SIRE 2.0 inspection are a tablet-based inspection, an enhanced question style, a unique inspection template, comprehensive inspector guidance provided with each question, a comprehensive observation reporting tool that includes graduated responses, and the provision of photographic content to support observations. So how will SIRE 2.0 with the risk-based approach enhance marine assurance processes? It will provide significantly improved data quality with a specific focus on processes, equipment, and people. More detailed, reliable, granular, focused, and comparable information. Observations that are set in a meaningful context to allow for analyzable root cause analysis. An integration of information records, including photography, the harmonized VPQ, PSC reports, crew matrix, and incident data. Expanding on the risk-based approach. Defenses, barriers, and safeguards occupy a key position in the risk-based approach. Systems on board have many defensive layers. Some are engineered, for example, alarms, physical barriers, automatic shutdowns, etc. Others rely on the actions of people guided by procedures and administrative controls. Barriers protect potential threats from becoming hazards. In most cases, they do this very effectively, but there are inherent weaknesses. In an ideal world, each defensive layer would be intact. In reality, however, they are more like slices of Swiss cheese, having many holes, though unlike in the cheese, these holes are continually opening, shutting, and shifting their location. The presence of holes in any one slice does not normally cause a bad outcome. Usually, this happens only when the holes in many layers momentarily line up to permit the trajectory of an accident to pass through, resulting in the threat becoming a hazard. The holes in the defenses arise for two reasons: active failures and latent conditions. Nearly all adverse events involve a combination of these two sets of factors. Active failures are the unsafe acts committed by people who are in direct contact with the system. They take a variety of forms: slips, lapses, fumbles, mistakes, and procedural violations. Active failures have a direct and usually short-lived impact on the integrity of the defenses. So often failures are blamed on the people involved in the task, and quite often, once these unsafe acts are identified, no further investigations for the causes of an adverse event are pursued. But virtually all such acts have a causal history that extends back in time and up through the levels of the system. Latent conditions are the inevitable resident weaknesses within the system which exist as a result of decisions made by designers, builders, procedure writers, and top-level management. All such strategic decisions have the potential for introducing weaknesses into the system. Latent conditions have two kinds of adverse effect. They can translate into error-invoking conditions within the local workplace, for example, time pressure, understaffing, inadequate equipment, fatigue, and inexperience. And they can create long-lasting holes or weaknesses in the defenses, untrustworthy alarms and indicators, unworkable procedures, design and construction deficiencies, etc. Latent conditions, as the term suggests, may lie dormant within the system for many years before they combine with active failures and local triggers to create an accident trajectory. Unlike active failures, whose specific forms are often hard to foresee, latent conditions can be identified and remedied before an adverse event occurs. Understanding this leads to proactive risk management. We cannot change the human condition, but we can change the conditions under which humans work. Bowtie methodology, on the other hand, is a risk model used to assist the identification and management of risk. All SIRE 2.0 questions were developed using this tool. This methodology is a core part of the treatment of risk, particularly where there is a high level of risk or where control effectiveness is assessed as low. A bow tie is a graphical depiction of pathways from the causes of an event or risk on the left to its consequences on the right in a simple cause-consequence diagram, where the knot of the bow tie depicts the top event and is the point where the pathways converge and the mitigation pathways spread out. The focus of bow tie analysis is either on the barriers or controls depicted to the left-hand side of the knot, or the top event that impact the likelihood of the event or circumstance, or on those on the right-hand side that address the mitigations of the consequences. It is used when assessing the completeness of controls to check that each pathway from cause to event and from event to consequence has effective controls. This enables factors that could cause controls to fail, including management systems failures, to be recognized. OCIMF developed bow tie models for several areas of marine operations to assist in the identification of priority threats and barriers that would prevent loss of control of activities related to process, personal safety, or reputational issues. The Inspection Working Group used bespoke bow tie software to map all activities identified with the loss of process safety within OCIMF bow tie models on tanker, barge, and terminal operations. As we know, the focal point of a bow tie is the hazard, which is something that has the potential to cause harm or trigger an event. However, for that to happen, something must occur that allows the hazard to evolve and result in the event taking place. The example of a hazard shown is volatile hydrocarbons under pressure in a pipeline, and the event is the loss of containment. The threats could be pipeline failure due to external corrosion or overpressure due to thermal variation or upstream emergency shutdown (ESD), the consequences of which could be fire or explosion, personal injury, and/or environmental pollution. After identifying the hazard, the top event, the threats and the consequences, preventative barriers can be identified. The process is repeated for the right-hand side of the bow tie, this time identifying controlling barriers to mitigate the consequences if the event was to occur. The focus of bow tie analysis is on the barriers depicted to the left-hand side of the knot that can change the likelihood of the event from occurring. These are proactive actions, or those on the right-hand side that can mitigate consequences after the event. This methodology allows the assessment of the completeness of barriers to ensure that each path from cause to event and event to consequence has effective control barriers, and that factors that could cause controls to fail, including management systems failures, are identified. The identification of areas of marine operations and the identification of priority threats and related barriers that would prevent loss of control of activities related to process safety, personal safety, and/or loss of reputation took approximately 2 years with over 100 participants from the OCIMF membership involved. Let's look at a marine-related example and the preventative barriers that can be put in place to minimize the risk of collisions, elisions, and groundings. So, what are the preventative barriers that we can put in place to minimize the risk of collisions, elisions, and groundings? You can see that 6 barriers have been identified. So, if we were using the Swiss cheese model, then, in this example, there would be 6 slices of Swiss cheese or barriers. Let's now take the first barrier, which is maneuvering the vessel clear of danger. The barrier is described in detail, and in this case, it states, The intent of this barrier is to ensure that the vessel is always able to maneuver clear of any threats or hazards. Just below the barrier description is a list of non-exhaustive barrier controls, such as what critical equipment and controls are in place to maneuver the vessel clear of danger: the main engine, steering gear, generators, ECDIS, ARPA, azimuth bearings, echo sounder, and anchor and windlass. These critical equipment and controls can be expanded into sub-barriers. Expanding on the navigational equipment, we get sub-barriers such as gyro error checks, use of passage plans, navigational audits, application of the rule of the road, effective lookout, use of tugs, UKC calculations, adhering to CPA, etc. So you can now see how the use of the bow tie risk assessment method allows us to identify and expand on each threat barrier. The level of granular detail to which the identification of priority threats and the implementation of related barriers was taken can be seen in this graphic. Let's summarize what barriers are all about. They are pivotal in preventing a direct link from a threat to a top event, a direct link from the top event to the consequence if the top event was to occur. They could be hardware in the form of technical measures, for example, equipment or structures. Process in the form of organizational measures, for example, procedures. People in the form of personnel who design, operate, maintain, monitor, and manage processes and procedures. Bow ties and barriers offer the following advantages. Risk-based decision-making. They allow the check on whether there are enough barriers to mitigate the risk appropriately. Barrier dependency visualization. They allow the visualization of what may happen if the resource responsible for multiple barriers is compromised, e.g. the chief engineer is ill or power is lost. Enables risk assurance. They allow a check on the performance of the barriers. Informed decision-making. They allow a check on what might happen if a barrier is removed or degraded. Risk-based management. They allow for the identification, analysis, evaluation, and treatment of threats and barriers. It is recognized that by identifying the correct barriers and testing the barriers for effectiveness, these barriers could be a highly effective method in monitoring the potential for a top event. SIRE 2.0 will not follow a standard question set for each inspection. A question library of inspection questions has been created to allow an inspection compiler to construct a unique, ship-specific set of questions for each vessel inspection, called the Compiled Vessel Inspection Questionnaire (CVIQ). All questions were ranked using the bow tie risk analysis to ensure that emphasis is placed on critical barriers and activities during the inspection process. This ranking of questions on the basis of risk allowed for each question to be assigned to the following categories. Core – questions that will be assigned to every inspection. These address barriers protecting critical activities. Rotational – questions that are non-core and are assigned to a vessel inspection in the following manner. Rotational 1 – every third inspection. Rotational 2 – every sixth inspection. Conditional – questions specific to the vessel, the operator, or the ship type that are based on data available for the vessel. These help to assess an operator's level of attainment against TMSA as declared by them in the Pre-Inspection Questionnaire (PIQ). Campaign – an existing rotational question assigned to every inspection for a fixed period in response to an incident or industry trend. Where no suitable rotational question exists, a new question will be developed for inclusion in the SIRE 2.0 question library at the next revision. Some facts about core questions. Core questions will be allocated to every inspection. Approximately half of the questions in the compiled questionnaire will be core. Core questions will be allocated for vessel type and operation, from information declared in the PIQ. Negative observations under core questions raised in the previous inspection will be detailed in the subsequent inspection. This ensures the weakness of critical activities are properly resolved. Campaign questions will be treated as core questions for the duration of the campaign. That concludes this video. In this module, we have looked at the following aspects of the risk-based approach to the SIRE 2.0 inspection process: bridging the gap between VIQ7 and SIRE 2.0 and the risk-based approach, the Swiss cheese model, bow tie methodology, question styles and how they were developed taking into account their risk ranking. Thank you for watching.